All right, so we're going to turn our attention to systems of equations now, and in particular, how to solve them. And there are three different ways we can solve systems of linear equations, and we're going to talk about the first method, which is graphing today. So by the time we're done here, you should be able to solve a system of two equations by graphing. Okay, some quick vocabulary for you first. What we mean by a system of linear equations is two or more linear equations, and it may be necessary to model a situation using two different equations at the same time. Okay? The solution of that linear system is any ordered pair that makes all of the equations in a system true. So we have to kind of figure out what we mean by making the equations true. So in order to do that, we're going to use a graphing method, and we're going to use the graphing method involving linear equations, so we do need to remember how to graph lines. So, quick review. We want to get this guy, number one, in slope-intercept form, which means we want to get y by itself. So to do that, we're going to subtract 2x from both sides. And then divide by 3. And so y equals negative 2/3 x. Now, this is lagging on me. 2/3 x plus 5. And so we want to go graph that guy. So the y-intercept is 5. So we're here first. And our slope is negative 2/3. So we go down 2, right 3, down to right 3. And then it's going to be really important to draw as straight a line as possible when we're using the graphing method to solve these systems. So you're going to want to grab a ruler or the edge of your calculator or calculator cover or your ID would be good to use. But draw straight lines, the best straight lines you possibly can. Okay? So anyway, so real quick, I always do sort of a review here of why we even draw these lines, right? What are these lines supposed to be telling us? And what students tend to forget is that this right here and the graph are connected. They're the same. They're the same thing. They're representing the same thing, just in two different forms, kind of like water and ice. It's the same thing, just in two different forms. The graph shows us all of the solutions that should be, all the points that should be solutions for our equation. If there's a point on the line, then that should be a solution to our equation. If we were to grab a point on this line and plug it into the equation, then it should work out, is what we mean by a solution. So we can do that real quick. If we grab, say, I don't know, this point right here, whose coordinates are -3, 7, and I plug those into the equation, I should get something that's true. Okay, so I'm going to do that, and I'm going to erase all of this, since now that we've seen how to get y by itself, I need some room here. And I'm going to use the original equation instead of the one that's in slope-intercept form. I'm going to use the standard form one because there's no fractions in there, and it's a little bit easier math. So I'm going to plug in -3 for x, 7 for y, and go work this out. So 2 times -3 is -6. 3 times 7 is 21. -6 plus 21 is 15. Now, since when I plug that point in, I get something that's true, that means that it's a solution to that equation. And that's what we're going to be looking for today, is solutions to a system. Okay? Can certainly do the exact same thing for this guy here. Want to get it in slope-intercept form, so I'm going to subtract x, divide by -3, and then I can go graph that where the y-intercept is 0, and my slope is up 1, right 3. And so there's our graph. Okay? All right. And again, this graph is designed to let us know what the solutions are. We should be able to plug any point on this line into the equation and get something that's true. All right? All right. So that's what we're talking about. If I want to find the solution to a system, now we're talking about a system of equations, more than one equation at a time, then I'm looking for a point that if I plug it into both, will make both true. For example, this system, we want to see if 2 comma negative 1 is a solution to this system. Well, pretty simple. Just plug it in and see if it works for both. So here I'm going to plug in 2 for x, negative 1 for y, and get 6 minus 2 equals 4, so 4 equals 4, and that's certainly true. But I'm not finished. I've got to check the other guy. I've got to check the second equation. So plug in 2 for x, negative 1 for y, and make sure it works here as well. So this is negative 2 minus 3. Negative 2 minus 3 is negative 5, so it works for both. So yes, this is a solution, but you've got to check both. Okay? All right. Same thing here. Plug those in and see if this, if 0 comma 3 will work for both these equations. Stop the video, plug them in, see what you get, and then start the video back up again and see if you're right. Okay? Did you get this? If you plug in 0 comma 3 into that x plus y equals negative 2 equation, then you can see, that 3 is not equal to negative 2. So 0 comma 3 is not going to be a solution. Okay? Now you plug in 0 comma 3 into this other equation, which I think was first in your notes. And it does work. Negative 9 does equal negative 9, but it didn't work for both, so it's got to work for both. Okay. Now, if you were number 3 in your notes, I should let you do, but if you plug in 1 comma negative 2, you're going to find out that it works for both, and there's definitely going to be a solution. And I think that we kind of get the point here. Okay. All right. So like I said before, the whole point in this is that there are some problems in some situations that call for a system of linear equations, so more than one. There are other ways of finding the solution, of solving systems besides graphing. We can use what's called the substitution or the elimination method, and we'll get to those in due time. But since, like I said before, since we're graphing lines, we might as well do the graphing method now. Okay, now, how does this work? The reason why I wanted to make the connection between the equations and the lines in our graphs before is because when we want to find the solution of a system using the graphing method, we're going to want to graph the lines. Well, how do we find the solution when we graph the lines? Well, since this blue line in the first situation here, right here, represents all the solutions to the blue equation, which we can't see. There would be an equation for that line. And the red line here represents all the solutions to the red equation, which we can't see. Then hopefully it makes sense that the point or points that would be solutions to both equations would be that point where they meet, where they intersect. Okay? So here, the graph is going to tell us that there's one solution. Here, there's not, in the middle guy, in this one, there's not any solution because the two lines don't meet, also known as parallel lines, right? And in the last situation here, infinitely many solutions, that's going to happen when our two graphs end up being the exact same line. Okay, now when does that happen? Okay, well, if there's one solution, the two lines will intersect at one point. When there's no solution, the lines are going to be parallel. When there's infinitely many solutions, the lines are going to be the same. Well, the lines are going to intersect when the slopes are different. So when we get these guys in slope-intercept form, then if the slopes are different, then there's going to be one solution. Again, another reason why we want to put these guys in slope-intercept form is that we can kind of foreshadow a little bit how many solutions there are going to be. If the slopes are the same, then our lines might be parallel. Well, they also might be the same line. So we have to check and go a step further here and say that, all right, if the slopes are the same and the y-intercepts are different, then the lines are going to be parallel and there's not going to be any solution. Whereas if the slopes are the same and the y-intercepts are the same, then the lines are going to be the same and there's going to be infinitely many solutions. Okay? So just kind of give us an idea of what we're looking for. So, to solve a system of equations, it becomes pretty simple. Put the equations in slope-intercept form. You can certainly do this using the x and y intercepts in the cover-up method, but like I just said, if you put your equations in slope-intercept form, then you're going to be able to predict how many solutions there should be for your system. Then we're going to graph the equations and then see where the graphs intersect. And wherever they intersect, that's going to be our solution. And it's imperative that we check our answer here. The graphing method is incredibly inaccurate and it's going to be really hard to come up with the intersecting point exactly. And so we have to take that point that we think is the intersection point and plug it in to make sure that it's a solution. Excuse me. Okay? So, for example, if I'm going to solve this system, then I'm going to get these two equations in slope-intercept form, which they already are, and then graph them. Before I graph them, I'll look at the slopes. The slopes are different, so they're definitely going to intersect, and so there's only going to be one solution. I'm only looking for one solution. So let's go graph them. Right? First guy, y-intercept, is down here at negative 12. This slope is 3. If I go up 1, 2, 3 over 1, 1, 2, 3 over 1, that's my line here. So there's the graph of that line. Okay, now the other guy. Start at 3 on the y-axis, and our slope is down to right 1, down to right 1, and so I would graph the line from here. Okay. All right. Now, this intersection point is not fantastic. So what we need to understand is we can actually use the slope for both lines to keep walking down the lines, and hopefully those slopes would put us on the same point. So for the first line, this guy here, and this is going to be the second line, if I kept using the slope from this point, I'd go up 1, 2, 3, right 1, and end up right here. And if I kept using the slope from the second line, from right here, I'd go down to right 1, end up at the exact same point. That should be my intersection point, and that should be my potential solution. So that point is 3 comma, 3 comma negative 3. Now, I'm only going to accept that as long as it's truly the solution. So I want to come over here and plug that into both equations and make sure that works. So for this first guy, negative 3 for y and 3 for x means that negative 3 equals 9 minus 12, or negative 3 equals negative 3, and that works. Now for the other guy, negative 3 for y, 3 for x. So we get negative 3 equals negative 3, and that works. And so now we know for sure that negative 3 comma 3 is indeed the solution. Okay? All right. And so number 5, same thing. I'll give you a second to get those in slope-intercept form and graph them, and I'll show you what you should get to make sure that you're correct. All right, we got to get both of these guys in slope-intercept form. First guy we got to do is subtract 3x from both sides. And we would get y equals negative 3x plus 11. And this next guy, we're going to subtract x. And I'll bring this guy down here. We get negative 2y equals negative x plus 6. Divide through by negative 2. And we get y equals, positive 1/2 x minus 3. A quick check of the slopes lets us know that there's going to be one solution to this guy because the slopes are different. So, we go graph. We go up to 11. We start here. And our slope for that guy is negative 3, so we go down 1, 2, 3, right 1. Go down 1, 2, 3, right 1. And we're going to want to draw our line through here. Okay? The next guy. Start at negative 3. And then our slope is 1/2, so we go up 1, right 2. Up 1, right 2. And hey, look at that. Using the slope here gets us to this intersection point. So the solution to this guy looks like it might be at 4, negative 1. And then, of course, we're going to go check it by plugging in. Okay. This guy here. Negative 1 equals negative 3 times 4 plus 11. So we get negative 1 equals negative 12 plus 11. And so we get negative 1 equals negative 1, and it works here. Now, we want to do the same thing down here. Plug in negative 1, 4 for x, negative 1 equals, half of 4 is 2, 2 minus 3 is definitely negative 1, so it works here too, and so this is definitely our solution. Okay? All right, next guy. Equation should look like this. And so I'll give you a second to graph those. Stop the video, start it back up again, and see if you're right. All right, so hopefully you looked first before you worked, because if you had, these slopes are the same, the y-intercepts are different. So this means that this is going to be two parallel lines, and therefore there should be no solution. Now, just to be thorough, I'm going to go ahead and graph these two lines anyway and see if I get two parallel lines. And so if I start down here at negative 9 for the first guy, and I'm supposed to go down to right 1, and I'm kind of, or I could always go up to right 1, up to right 1, and start to get my line from here. And then the other guy who started at positive 3, and the slope is negative 2, so I end up here, here, here. And they don't really look parallel, but that's probably more because of my graphing than anything else. Okay, but they certainly don't intersect within the grid, and since I did my examination of the equations, no solution definitely seems reasonable. Okay? All right. Next guy. Try this guy, stop the video, see how you do. All right. So, oops, sorry. Get this into slope-intercept form. Subtract x, y equals negative x minus 2. And then, let's see, this guy, subtract 2x from both sides. So you should get negative 3y equals negative 2x minus 9. Can I divide everything by negative 3? And we get 2/3 x plus 3. So let's go graph these two guys and see what come out. Well, look at the slopes first. Slope here is -1, slope here is 2/3. Different slopes, we should have one solution. So, we start at -2. Go down 1, right 1, because the slope is -1 for that first line. And we want to draw a nice straight line. Just like so. Now, the next guy, we start at +3. Slope is 2/3. So we go up to right 3, up to right 3, and we can draw our line from here. Okay, but again, we can use our slope to walk to our intersection point. Now, the graph of this second graph number 2, the slope was up to right 3. Well, I can go down to left 3 and get to that point. And then the slope for the first line was -1, so I had to go down 1, right 1. Well, I can certainly go up 1, left 1, up 1, left 1, and I end up at this point again. So that must be my solution point. So at -3, comma 1, I think that's my solution. Now again, I'm going to want to check, plug it in and check. So over here, I plug in 1 for y, -3 for x. This becomes 3 minus 2, which is certainly 1. So 1 does equal 1. And I'm going to plug it in over here. 1 equals 2/3 x plus 3. Oh, sorry. Plug in -3 for x. Do some cross simplifying. This is -1. 2 times -1 is -2. Plus 3, and this ends up being 1 equals 1, so this is our solution. -3, comma 1 is our solution. Okay? Great. Got another one here. Let's try this guy. Again, stop the video, give it a shot, see what you come up with, then start the video again, and see if you're right. Okay, so what you should have come up with is right here. Okay, those are your slope-intercept forms of those two equations. The solution point should be 6, -2. If you plug both of those in, you will end up getting two things that are true, two statements that are true, so it should work out. But you make sure you're checking your answers. Okay? Now, got one more. So take a look at this guy. And stop the video, come up with your graph, and see how you did. Okay? Should have come up with this. By the time you get the second guy in the slope-intercept form, you've got the exact same equation. So you're going to have the exact same line, and your solution is going to be infinitely many solutions. Okay? All right. So when do we use a system to model a situation? Well, here's an example. At Gary's gym, he offers 2 payment options. Option 1, you just pay a monthly fee of $26. Option 2, you pay a one-time $50 membership fee and then $20 monthly after that. After how many months does it make sense for you to become a member of the gym? Write a system of equations to model the situation. Okay. Well, here's the thing. We don't know how many months we're talking about, so I'm going to let x be the number of months that you pay for your membership. Number of months paying. Okay? Well, Then what we also don't know is how much going to the gym costs. So we actually do have two variables here. Well, how do you get the cost of the first situation, where you're just paying $26 a month? Well, hopefully you're saying to yourself, well, just take the number of months that you pay times the fee, and that'll be your total cost. So we would take 26 times x, or just get 26x. The second option means, so to get our total cost for the second option, we have to pay a one-time $50 membership. So we're still going to pay a monthly fee, but now the monthly fee is $20. So we take 20 times the number of months that we pay to get your total cost, but we have to add to it the $50 that we had to pay up front. And so what we would want to find out from here is what number of months in total cost would you come up with to where these two options were the same. Okay, we'll talk about solving these some other time. We just want to get into the habit of writing these equations to model these situations. And so there's 10. Okay, try 11. Read through that and see if you can't come up with a system to model the situation. So stop the video, bring it up when you're done, and see if you've got the right answer. All right, so what'd you come up with? Suppose a puppy weighs 5 pounds at birth and grows at a rate of 1/4 pound per month over the first several months. Another puppy weighs 4 pounds at birth and grows at a rate of 1/2 pound per month. After how many months will the puppies weigh the same amount? Okay, two variables again, because we don't know the number of months that we're talking about. So the number of months growing is going to be x. And the total weight depends on the number of months that you're talking about. So we probably ought to have a conversation about dependent and independent variables, but the total weight is going to be y. So in the first puppy, the total weight is going to come from the 5 pounds at birth plus the 1/4 pound per month. So we've got to take 1/4 times the number of months that the puppy's growing. So 1/4 x. Now for the second puppy, it's the same thing. Total weight is going to be equal to the 4 pounds at birth plus the 1/2 pounds he grows per month. And so there's your two equations. Okay? All right, hopefully that makes enough sense. Your homework is out in Canvas. Make sure you have that done in its entirety by next time. Next time will be our test.